So how hazardous is that nuclear waste that's produced in a nuclear power plant? So the chart here shows three different curves, green, blue, and red, depending on how you process the waste when it comes out. And this is normalized hazard relative to naturally occurring uranium, which is at 1. So at the left-hand axis, the green curve for advanced reprocessing of the fuel is 10 times more hazardous than natural uranium ore. So the process of burning this stuff in a nuclear reactor makes it a more hazardous substance. The byproducts of that nuclear reaction are more hazardous than the natural uranium, and in some cases, dramatically more hazardous, several thousand times more for the blue and the red curves. And notice that this is a log-log plot. Each increment on the vertical axis is a factor of 10, and each increment on the horizontal axis is also a factor of 10. So even with advanced reprocessing, it takes 10 to the 3 or 1,000 years for that waste to reach the level of hazard of naturally occurring uranium. And for standard reprocessing, just burying it, the red curve, 1,000 years from now, it's still several hundred times more hazardous than naturally occurring uranium. And it's not until 1,000,000 years after you take it out of the reactor that the toxicity has dropped down to the level of natural uranium. Well, let's compare that hazard to the hazard that we actually are experiencing from nuclear reactors and nuclear waste to other sources, naturally occurring sources of radiation. Now, of course, this is not comparing to what would happen if you broke into a nuclear waste storage facility and stole some of that material and made a decorative fixture for your dining room table. That would be worse. But in terms of the amount of radiation that is released currently from these different processes, you can see that in the United States, nuclear power is a tiny, tiny fraction of the radiation that we receive. So the other category, 0.65% in the United States, 0.33% worldwide, is where radioactive uh, impacts onto humans comes from nuclear power, including the waste and nuclear weapons tests. Half of the radioactive exposure, radiation exposure that people get in the United States is from medical procedures, and nearly a third is from naturally occurring radon, which, depending on where you live, is present in the air. And in some parts of the country, you go to a hardware store and buy a radon test to make sure that there's not too much of that leaking into the air in your basement, for example. Uh, you also get hit by radiation from cosmic rays coming from outer space. Uh, so at the present time, nuclear power plants, nuclear waste, nuclear fuel are an insignificant contribution to the total amount of radiation exposure for people. And if we take a look of a coal power plant and a nuclear power plant, both at 1 gigawatt power equivalent, so just comparing comparable power plants, and look at the environmental impact. Remember the picture of the coal train, 100 cars with 100 tons of coal, each car once or twice a day compared to a truck every year or so of uranium. So the fuel consumption is much less. The amount of pollutant going directly into the atmosphere is much less. Carbon dioxide emission is zero for a nuclear power plant because you're not chemically burning anything. You're not oxidizing carbon as you are in a coal burning power plant, 1,000 tons of CO2 emitted per year. The solid waste, 30 tons of coal ash per hour compared to very toxic radioactive waste, but at a level of 20 tons per year instead of 30 tons per hour. The land use is much less because you're using less fuel and you produce less volume of ash. Interestingly, coal has some radioactive products in it as well, but it's about 50 times more radiation release from nuclear power plants than from coal. Then there are other hazards that we sort of take for granted or don't really pay attention to, such as fatalities involved in mining. There are several times higher rate of deaths attributed to mining of coal than there are from radiation. And then by looking at the radiation from nuclear power plants, you can say, well, it's a certain increase over the population. That's about one additional death per year from cancer uh, caused by radiation from nuclear fuel, nuclear use. On the other hand, from fossil fuel burning power plant, coal power plant in particular, it's about 100 times that number of additional deaths from air pollutants and their hazardous effects. So here we see a nuclear power plant. This is the 3 Mile Island nuclear power plant that had an accident with a meltdown in 1979. The most famous, one of the most famous nuclear accidents was the Chernobyl accident, where there was a meltdown and a big release of radioactive material that did kill many people. And that site remains very hazardous and toxic to this day. You can see on this chart the sort of map of the spread of the radioactive material in the smoke resulting from the explosion in that nuclear power plant. And then more recently, the Fukushima nuclear power plant in Japan was damaged by an earthquake, and that prevented the normal cooling of that and resulted in some release of radioactive material as well. So, like everything, it's a somewhat complicated picture. If you just add up the numbers, the health hazards of nuclear power at the moment are far smaller than the health hazards of fossil fuels. The advantages of nuclear power over fossil fuels are there's no greenhouse gas emissions. The total volume of waste material that's produced is much smaller. The total volume of pollutants going to the atmosphere is much smaller. But there's a definite visceral fear associated with nuclear waste and radioactivity that maybe has something to do with its invisibility, and there's something scary about it. For some reason, that's more scary than the pollutants that are produced by burning fossil fuels, which also frequently are invisible and we inhale them and can also provide give us fatal diseases. Because it's critical to avoid a big accident like we saw at Chernobyl or 3 Mile Island or Fukushima, making a safe nuclear reactor is critically important and also very expensive. At the moment, nuclear power sources are less than 10% of US energy. So you can see on the left the US supply, and on the right, figure B, is the world supply. And so nuclear is about 8.5% of the US energy supply as of the time of this figure, which is around 2015 or so, with gas, oil, and coal, the fossil fuels, making up more than 3/4 of the energy supply. Over time, the percentage of energy coming from nuclear power peaked in the 90s and has been dropping steadily since then, and it's probably going to continue to drop unless there's a real change in policy that makes it more economically viable to construct additional nuclear power plants. But even then, as you can see from the plot here, over the course of the next few decades, it's not ever projected to be more than about 10% of the power supply. The last part of this module in this chapter talks about nuclear fusion, and I'll let you read about that. I'm only going to say that nuclear fusion remains technologically very challenging and is not currently a viable source of getting energy. It is the nuclear fusion is the nuclear process that takes place in the insides of stars. So ultimately, all our power on Earth, except for tides and geothermal, is coming from nuclear fusion in the interior of the sun, which produces light, which radiates away from the sun and makes it here to the Earth. And nuclear fusion is not the splitting apart of atoms, but the assembly of atoms into new, heavier atoms. So in the sun, hydrogen fuses into form helium, and as it does so, it produces additional energy. The mass of this helium nucleus is a little bit less than the mass of the four hydrogen nuclei that went into making it. And there are technological attempts underway to create nuclear fusion that produces more energy than was required to make that fusion take place. But it's much, much easier to take an unstable atom and let it break apart than it is to take two atoms that are positively charged and really don't want to stick together and force them to get so close together that they fuse and go through that process. So it's an area of academic research at the present time, including some large-scale technological experiments, but it is not in our energy picture, and so we won't be saying anything more about fusion.